In the previous class, previous hour, we have seen that how to solve an algebraic equation using the perturbation methods, and you know that it's comparison, right? So then comparison shows that it is a very good agreement between the exact solutions and approximate solutions. And what is the lesson from that? That if you go the epsilon smaller and smaller, then the exact solution match with the perturbed solution. So this is the understanding from this analysis. So hence, can we believe perturbation methods, regular perturbation methods? Can we believe or not? Can we believe? Mritika, tell me, can we believe or not? It is a proof. Here is a proof. We need the proof, and the proof is here. So hence, we can believe the perturbation methods of this type of expansion, and we can proceed, right? And then it is valid only when the epsilon terms are smaller. Okay, right. Now, if you take one more example, this is the example, and then and here is we take the expansion for this is x. So epsilon here is what it is coming, that is it is not connected to the highest power of x. So hence peacefully we can use the regular perturbation method, in which the expansion is taken as follows, and then we will have here is it is unperturbed solution. When you get for epsilon 0 you get it, but you have two values here, is one is 0 and 1, right? So you can solve from this one, you can find out what is the solution. That is you have here is right. So if you use epsilon 0, you have that is x square, and this minus 1 is 0, implies that x equal to 0, and other is say x equal to 1. Okay, here is we have. So then you can start your perturbed solutions with either you can choose x naught is equal to 0 or x naught is equal to say 1. Either you choose this is try to go to expansion x epsilon is equal to, first one is 0, for example a naught, this let us call a naught, and then next one is epsilon a1 and plus I write everything here is a naught plus epsilon a1 plus epsilon square a2 and so on we have in that. So in which what happens, you can choose x naught is equal to a naught is equal to say 0, and then you get the result corresponding to your the 0. Okay. So similarly, you take suppose that if you take say x naught is equal to say 1, if you take x naught is equal to 1, your expansion will be x of epsilon is equal to 1 plus epsilon a1 plus epsilon square a2 plus so on. Now your job is to find out a1, a2 and so on. Okay, but it is very important thing is we have to focus on the terms like a naught and epsilon a1, epsilon square a2 and so on. If you want to get the bounded solution or convergent solution, so in such case what happens, this term should be smaller than this term. Do you agree or not? The question is, suppose you want the bounded solution, convergent solution, okay, because epsilon we having, and then in such case this term must be smaller than this term. Do you agree or not? Next, similarly, this term must be smaller than this term. Do you agree or not? Right? For example, if you see the power series 1 by n square, so 1 plus 1 by 2 square plus 1 by 3 square plus 1 by 4 square and so on. This is your well-known power series, right? And then tell me that this term is, if you want to say this is a series is converges, if you want to say, in that case this term is smaller than this term. Do you agree or not? This term is smaller than this term. Okay, and let us call this is a naught and this is a1, this is a2 and this is a3 and so on. In such case is what, a1 is less than a0. Agree? Right? And similarly your a2 is less than a1 and then a3 is less than a2. Suppose if it happens this way, so definitely the series going to give the final value. If you add infinitely many terms of that expansion, you are going to get the final value, right? This is what we have. So similarly, same idea we apply here, that is to get the bounded solution. To get the bounded solution, what we do, that is this term must be smaller than this term, right? And similarly, this term must be smaller than this term, and other term must be smaller than this term. If it happens, keep on decreasing. decreasing order, so definitely you will have the that is bounded solution. Okay. Now here is some important observations are here. You can see that these numbers you should have, that is in, of course. Let us see what the expansion is. So x of epsilon is a0 plus epsilon a1. This is asymptotic expansion as earlier. And what you have to find out? A1, A2, A3 you have to find. What about A0? What about A0? A0? A0 is you have already chosen here, either this one or this one, any one. Okay. So then one of A0 we have already with the whatever you having that unperturbed case. So here is these numbers should have the order of A0. So hence epsilon A1 should be smaller correction of A0. Epsilon square A2 should be smaller correction to epsilon A1 and etc. If it is like the decreasing order, so definitely your whatever series is going to converge. Okay, that is one thing. Okay, let us take this expansion into the equation 1 here and here. If you submit that and then equate the like powers of epsilon as earlier, right? So in that case, we get the sequence of the equations. This is first equation and this next equation. This is okay. And suppose if you see this epsilon and epsilon square and epsilon cube, for example, epsilon 4. First one could be if you take first one is A0 you have, right? A0 means what? Epsilon power 0. Okay, this is epsilon and this is epsilon square and this is say for example epsilon cube. You see epsilon power 0, epsilon square for this expansion. And the first one is what? A0 minus 1 you get. Okay, first one. Okay, so here is you have this is okay. Next epsilon case, what happens? Epsilon case you have that is 2 A0 minus 1 and A1 is equal to minus 1, the next one. And if you take other one, 2 A0 minus 1 and A2 is equal to minus A1 square minus say A1 square, okay, and so on. So you can see the observations here. From the first thing, you can find it is nonlinear equation, right? Nonlinear equation, and from this one, what is the A0? You can find out either 0 or A0 is 1. So we choose 1 here. And if you take that, submit here, so you will get what is A1. How to find A1 here? How to find A1? So the simplest that your A1 value is equal to minus 1 divided by 2 times of A0 minus 1. Do you agree with this? This is right. Okay. It means what? You know A0 value, submit here, you will get this. This is a rule same for the differential equations also, keep in mind, right. So similarly, and from this is also you can say A2 you can find out minus A1 square divided by 2 times of A0 minus 1. Okay. So you know A1 from the previous step and submit here you get A2. So hence what happens, you find out what is A0, A1, A2 and so on, all the values you find out and you can get it. Okay. So then what happens, by seeing that you can see, so this is the term is fixed, 2A0 minus 1 fixed here also 2A0 minus 1, and coming also you will get a similar way. Okay. So in such case, why not you write it is in the general case as L is, let us call L as operator this. In the case of differential equations, L is operator, and that is operating on this form, for example, and this is equal to, it is equivalent to 2 A0 minus 1, which is operating on 1. What are the things coming here? Okay. It is same for the case of differential equations. Differential equations also you take the epsilon coefficient equal to 0, epsilon square coefficient equal to 0, epsilon cube coefficient equal to 0, you get the system of equations. You get the system of equation, right? So then what happens, you write that L of this is equal to whatever we have this is, okay. Then how to find this is the value of this what are the terms coming here. So you take this is equal to you write that whatever we having something divided by say L, something divided by L. Is it not? Do you have experience or not? This is something divided by the operator L. Are you able to catch this point? So accordingly, you can find out the what are the values coming here, A2, A3, A3, A4. For example, if you are having say L0, W0 is equal to say N0 if you have, okay, or if you want this is L0, W1 equal to N0 you have. This is differential equation. right? It is similar to this. Okay. Then how to find W1 here? W1 is N0 divided by L0, which is like this. So the idea, whichever we have algebraic case, is same for the case of the other. That is reflecting here, and accordingly what happens, you can find out the values and submit here. And if you submit this, so you will have this sequence of these equations. Okay, homogeneous. First one is of course it is non-homogeneous, and the second one is again we having A2 case. And then if you see the brackets, so having this operator type. Okay, and accordingly you can solve if you choose A0 equal to 1, right? And then leading our term A1, A2, A3, all the terms can be traced out. And then suppose that now find the values of x epsilon for 0.1, 0.01, 0.001, etc. If you submit these epsilon values into the expansion, okay, then you can get the corresponding the solutions. Of course, as like this table you can create, and accordingly you can find the solutions. Okay. And if you like that, I can ask to the system that can I try this? I don't know. I don't know whether I can use it or not here. Christian, the net is coming. Okay, then not to worry about it. Yeah. I will take a letter. This experiment, not now. Okay, so in this way, we try to find out the solutions of the algebraic equations. Okay, let's try to keep these points in mind, and then let us go to the next thing is that. So then we have that is weakly nonlinear boundary value problems. For example, let us take as an example, and assume that this is an equation. Okay, equation which is first order equation, which is example of Riccati equation. You know, the Riccati is very famous nonlinear equation, and then has the applications in the boundary layer models and so on. Okay, so let us see, this is the equation, and here is first order differential equation, you know, and then epsilon is the small parameter is added to the nonlinear term. It is one of the assumption, and which is equal to t. So then so it is a nonlinear or ordinary differential equation. Of course, t is what it is. So let us take time, then dot we can put, or t is any variable means we can have the dash here. So finally we have a differential equation, and then with the condition is there, with this initial condition we can have it. Okay. Okay. So maybe initial or maybe boundary, whatever the case. So we can take, but the idea is what t is taken as between 0 to 1. And epsilon is very small quantity. So then we had to solve this type of equation. Then can you tell me that how to proceed? This is the example of regular or singular perturbation. Regular perturbation. Very good. Because epsilon is connected to these some other terms, but not your higher order derivative term. So very simply you can tell, and then you can go here. Okay. The problem is nonlinear problem, and it is also a non-trivial problem, we can say. The corresponding unperturbed problem, when you get, if you submit epsilon value 0, suppose epsilon 0, then what happens? There is no epsilon, no perturbation. So then no perturbation means what? Unperturbed problem we can tell. So we have this unperturbed problem is there, and this is a differential equation, ordinary differential equation, and with the condition, and then you can simply solve this equation. And this first order, we need how many conditions? Only one condition required, which is present, and then we get the unique solution, and unique solution for the unperturbed problem. This is nothing but your U0. Okay, how to find the leading order term? By putting epsilon equal to 0, keep in mind this point is very important. How to get the solution for the leading order U0 or initial value U1. So for that, put epsilon value 0, and then I can find the solution. You have seen already here. So here what happens? How to find the leading order means what? A0 how to find? Put epsilon 0 here, then find out what are the x values, right? Like x0. So similarly, the same rule here. How to find unperturbed solution? Put epsilon 0 here and find the solution, and then this is the unperturbed solution. This is what we have. And then we had to go to understand to solve this complete nonlinear problem using that regular perturbation. And as earlier you have done the expansion, here also same expansion in terms of the epsilon. Okay, independent variable is t here, but it is expanded with respect to epsilon value. But keep in mind that epsilon is very small. Same idea, expansion. Then what you have to do that is you have to submit this into the differential equation, and similarly we need the boundary conditions. So here is what we have the expansion, whatever u is taken here, u0 and epsilon u and something. So instead of t you submit as initially say 0, and then we have this is equation. Okay, 1 minute. Okay, right. Okay. So then what happens here is this is 0, then not 1, some mistake here, it is 0, here is 0. So then only what happens, we get this type of the solution, expansion. Okay, this expansion we having, t value is 0, initially we have this. So compare left and right. So then what happens, we get the u0 of 0 is 1 and u1 0 is 0, u2 0 is 0 and so on. So we have all the things here. And then for the case of differential equation, compare this system of equation, we get this is non-homogeneous linear equations. These are non-homogeneous linear equations. So it means what? So instead of solving whole equation, so it is better to solve, better to convert into the that is non-homogeneous linear equations. It's better one, simply, okay, as earlier. And then we have this is equation, differential equation with a condition, differential equation with condition, differential with condition. And accordingly, so we have the solution here. This is the first order solution, and u1 value will be taken in this manner. Okay. Then previously we know what is u0. We know u0 we know from here. u0 we know from here, and then u1 will be understood with the help of this second equation. Second equation, if you solve that, and you get the u1. Suppose that if you combine both this u0 and u1, and this is solution u. So finally, what is, you can check that is epsilon u1 is less than u0 t, and this solution you can take. So this is the way we try to proceed to get the solution. Okay, and then we get these better solutions for the range of epsilon is positive. Okay, in this way we can go. So this is way the same procedure for the algebraic, same procedure for this we can have. And we can go to the next model is van der Pol oscillator. Van der Pol oscillator. So for that again, this is the equation we have, and here is epsilon is a nonlinear that is a parameter is introduced. It is again example for the regular perturbation problem, and then unperturbed case. Yeah, unperturbed case, epsilon 0 is submit here, you get this equation, and this is the solution for the problem, right? This problem solution A and phi, these are the constants we need to find out using your conditions given for the model. Here is condition not presented, and then so we have that is if you want to improve this approximate solution, because if you take complete equation, so you have to take the help of this type of expansion as earlier. And then if you submit this expansion into the equation, this equation, and then you receive this type of the expression, and expanding this epsilon both sides left and right, simplifying this is, here is no epsilon and epsilon quotient, epsilon square quotient left side, right side is epsilon, epsilon square and epsilon cube quotient, and then you can compare those things to have the system of equations. Epsilon power 0 left side, you can see that epsilon power, this is we can call as epsilon power 0 quotient, and accordingly here is, do you have any epsilon power 0 terms here? Right side nothing. So hence, so you have this is right side is 0. Okay. So similarly left side is what? Epsilon quotient is, this is the term, and right side is epsilon quotient, this is the term. If you compare both sides, then you have the next, this is left side and right side, and then for the epsilon square we have this is left side and right side we have it. Now the problem got very simplified. So instead of taking the whole problem, this is the solving nonlinear problem. It is really very tedious, very tedious. So why not you go to the perturbation problem methodology? You have system of simply homogeneous equation, homogeneous and non-homogeneous linear equations, and you know the methods, and you try to solve them from the first equation, linear this model and homogeneous, and previously you know that from here is leading solution u0 it is, and then from this you can get the same solution, and go to the next epsilon. So you submit here whatever you get from this on the right hand side, and left side is what u1 you have to find out, and similarly u1 and u0 from these two above equations, submit on the right side here, and you know the right side non-homogeneous linear equation, and you can solve. Okay, if you see this this sequence, firstly you can see that yeah, you can see the left side is what? Left side is you have, left side is what? D plus 1 operating on u0 equal to 0. Okay, from this first equation, right. Next thing is d square, yeah, d square. Next one is what? You are having d square plus 1, right, operating on u1 is equal to, you have something non-homogeneous part, and similarly other one, if you take again d square plus 1 operating on u2 is equal to, again you have non-homogeneous part. Okay, it is similar to this one, you can see here. For the algebraic case, you have seen 2a0 minus 1, 2a0 minus 1, 2, and again another one also we get the same way. And here also you can say d square plus 1, d square plus 1, d square plus 1, right. So like that we have the operators, right. And how to define the values of u1, u2, u3 here? Simply send this operator to the denominator. So it means what here, if you want to find say u1, u2, then what you have to do? So you have to do that is u1 you will find out something divided by, what is that? D square plus 1. Okay, so here also if you want to find out this is u2 from this, something divided by d square plus 1. That's all. Okay, that is going to give you particular integral, right? If you divide by some operator, you will get the particular integration. So we don't get here is we don't prefer here the complementary. Actually, it is non-homogeneous model. It possesses the two solutions like complementary function and particular integral. That is we aware of it. But due to this one, whatever the conditions are there, initial conditions, and what is the operator, we see that for everything d square plus 1, d square, same operator is there. So we try to neglect the initial conditions now. Remove the initial condition. Okay, don't consider initial. Be careful. Initial condition. I am not saying about the boundary conditions. Initial condition, time dependent condition, remove it. Okay. So in such case, what happens? So we can find simply there is no complementary function, but you have only the particular integration. Okay. So we have the particular integral solutions are here, and you can work out with that. Okay. This is same thing for all these regular perturbation problems. Okay. And then you can see here. So next thing is okay. From this is u0, as we have seen, that is what the solution a cos t plus 5. I hope so you know how to catch the solution, because you know that d square plus u0 is 0, right? And then you can assume the solution like a into e to power of something, e to power of m into t, you can assume, right? The solution u0, you can write that is a into e to power of m into small t. You can have this, submit here, and m values will be, what is that? Plus or minus I, plus or minus I, and submit back here is plus or minus I, and simplify that. So you can receive cos function. You can write it in terms of the cos you can write it. Okay, and then we know u0 value, and then take the next equation to find out this is from this u1 by taking the what type of integration we need, particular complementary from the second equation. It's non-homogeneous equation, but right side we know that only just particular. That's all. According to this one, according to this, just to go for the only particular integration, no complementary. Okay, that is one thing. So like that, so we know that is the u1 will right side. If you simplify that, you will get like this. And then of course, if you want to proceed further, so you have to do some simplification, and you have that is right side is in this format, and then we need the particular integration if you find out. So then we have this solution. You can see t times of cos t plus 5 minus 1 by 32. This is okay. Now here your u0 is what? Bounded solution, right? It is a trigonometric solution. Agree? It is a trigonometric solution. It is okay, periodic function. Okay, but whereas if you proceed further, so then u1 has two parts. One is it is t connected to the trigonometric function, and then here is no t. It means it is periodic function. So here among the which is periodic function, which is not periodic function, can you tell me? Among these two, which is periodic function, which is not non-periodic? Second is periodic function, obviously. The first one is non-periodic. So hence what happens now, as t is what? T is time here. For example, if time keep on increases, then due to this t, then everything try to increase and increase and increase, because this is bounded function, cos function is bounded. But due to the presence of t, as t tends to infinity, this value keep on increases, right? So then what happens in such case, u1 will be unbounded solution. U1 will be unbounded solution when t is large. So in such case, what happens? Our solution, whatever methodology we have, that is fails here. Okay. In that case, what happens? This type of terms are known as secular terms. It is called as secular terms. So we have to remove these secular terms by using some other methods we have to consider to solve this type of things. Okay. So this is this type of methods we are having, that is a straightforward method. Actually, what we do regularly, method of straightforward. So our BSc or degree case, what happens? We try to put t times of something or x times of something, we get it, and then what happens? This is becomes as unbounded, and then just we write down that only. Okay, but we don't classify that whether bounded or not. But here is what, as t increases, this is becomes unbounded. Unbounded. So hence what happens? It is we cannot proceed in this way. This type of methodology we call as method of straightforward. Okay, so when it is fails, then we need some other kind of methods are required. Other methods are required. Okay, let us see here. Finally, we get approximate solution by substituting the solutions obtained from the 0th, first, second, etc. into the following equation, and then we get this. Okay, and here is what you can start with the epsilon u1, epsilon square u2. With that, we also you can start. It means what here is started. The solution is what? It is started as a u is equal to u0 plus epsilon u1 plus epsilon square u2, okay, and plus so on. In this way you can take. In this way you can take. Otherwise, you can also take that is u is equal to epsilon u1 plus epsilon square u2 plus epsilon cube u3 and so on. In this also you can take. That is also gives a solution. That is why it is called as asymptotic expansion. It means at basis we are taking. Random we are taking and we are checking whether it gets or not. Okay, so this is happens here. So then the next one is, so this point try to keep in mind, that is first term is free from epsilon, second term is having the epsilon and so on. This is our assumption. Okay, if Krishnendra wants, okay, he can start with epsilon u1, epsilon u2. He can take and submit it to the equation. He can get this similar type of solutions. Okay, so let us see. Of course, this is exact solutions diagram. If you plot that, we get for different values of epsilon. This is where we can get it. Okay. Then okay. So okay, what happened? So this is expansion we have done with the help of epsilon. But whereas in the case of your power series method, you try to expand the solution in terms of x power. Is it not? Your differential equation includes x as independent variable. We write what? The solution is y of x is equal to summation an x power k plus m, right? So like that we try to expand. This is we have it. So this type of expansion we call as a coordinate expansion. So if you take coordinate and take expansion, then how it looks like. So that is we have this type of if you take the differential equation of Bessel's differential equation. So then in that case we take this type of expansion, usual expansion. Okay, here who is expanding? There is no epsilon. We don't have any epsilon here. Okay, here we have coordinate x. So power of x we are expanding. We need to find out what is the mu value, what is m value. These two things we have to identify. What we do there. Okay, recurrence relations we get there. So we try to work out that, but here is I'm not stressing too much. So and these things everything you know, and in this way we try to get the solutions. Okay. Okay, another one of the example. So this example can have this something. Okay, now very important things about these symbols we have, Latin symbols. Okay, we write that is a Taylor series expansion. Okay, Taylor series expansion we write. How to write that? So here we stress that is say f of x naught plus h and h is small, f of x naught plus h f dash x naught and plus h square by 2 factorial f double dash x naught and plus and so on. So we try to write, otherwise we write this is as order of say h power 3 and h is small. Okay, h is say 2 less than 1. So we can write that, and here is this is dominant term and other terms are that is we can say correction terms we can write here. We can say here. Okay, let us see here. So then in that case then how to say it is if you write f of epsilon is equal to, for example, this is one thing, but let us focus on this. F is function expanded with respect to epsilon, and you are calling this is say g of epsilon. What does it mean? F is of order g of epsilon. F is we have one function of order g of epsilon. So what does it mean? That is as it means that is as your epsilon is becomes small and epsilon is because for this 0.1, 0.01, 0.001, if it is like that. So in such case, what about this ratio f of epsilon divided by e of epsilon? So that is always say bonded are immediately as epsilon changes, so then accordingly the fraction f of epsilon. Okay, so then let us see in some example. Let us see. So sin epsilon is of order epsilon out of epsilon. What does it mean? What does it mean? If epsilon is smaller, what is the sin epsilon expansion? Can you tell me? That is epsilon minus epsilon p by 2 real and epsilon power pi by 2 real and so on. This is the we are calling that this delta is equal to epsilon. It's possible. Epsilon is small. Epsilon 0.01 for example or 0.02. If epsilon is 0.02. So here is epsilon equal to 0. 0 means what? You can start with 0.1, 0.01, 0.2001 and so on. If you do that, if you take this sum, okay, this sum becomes too small, right? So the impact is very small because it is epsilon of 5 and so on. All the sums impact is very small. So essentially this way is good. Right? When epsilon approaches to 0. So then the left side is equal to what happens. In that case, we write that f of epsilon is of order g. I hope you understand. Right? Epsilon should approaches to 0. Not general case. So if you take epsilon will 0.1, so sin 0.1 is not equal to obviously 0.1. So that is this is very important in the limiting case of epsilon. So this fraction, right? So that is always important. In that case, we say that this is of order. Sometimes we say that the amplitude is of order epsilon. The finite amplitude is of order epsilon. What does it mean? Means this fraction must be important. Or in the limiting case of epsilon, it is very important. Limiting case is very important. So all this is you can trace out. You can trace out that is sin 7 value equal to epsilon. Whenever epsilon is small, and all the things. Okay. So this is the symbol we have in the capital O. Answer. Right. So similarly, let us take this is another one. Small O is also there. So in that case, what happens if it is up to 0 in the limiting case, f of epsilon by g of epsilon is equal to 0 as epsilon is 0. So then we can say that f of epsilon is of small O of the epsilon. So these symbols we need important to use for the text. So we write this instrument. You see here, f of epsilon equals small O of g of epsilon means that f of epsilon is much smaller than g of epsilon. They agree at numerator is smaller than the so in the limiting case, limiting case is very important. Okay, right. So these are some examples. You can say sin epsilon is equal to order 1. It means what? The fraction not a limiting. No. So that is zero. They agree or not? Sin epsilon by 1 is 0 when epsilon tends to 0. I agree with that. What is it? Sin epsilon by 1 is it takes 0 value, then what? In such case, we write it in this notation. Okay, so like that, these are some of the examples using this symbol small o, capital O, and small o. These are very important in the case of your convention. We can refer that. Okay, then you can try that. So then I like the important methodology. We have some other methods also there, like when this method, straightforward expansion method, failed, right? So then we have some other methods also there. It is called the leadership point method, right? Leadership point method. So in which whatever we have in t, whatever we are taking the t the variable. So instead of t, we take the scaling as omega times of t. We take omega times of t, and omega it is expanded as omega naught plus epsilon omega 1 so on. So it is taken this it is a parameter. It is a parameter. Is expanded as omega naught epsilon omega 1 this is, and whatever the unknown variable is there. For example, u x t comma epsilon. So t comma epsilon that is expanded as u of tau. Okay, u of tau and plus u1 of say epsilon we had epsilon u1 of tau and epsilon square u2 of tau you take and so on. So you take this step of expansion, summation of the process, right? So then in such case we will try to get the that is validity solution. It means what we get the bounded solutions. Okay? If you take this, what is that? You have usual t is a variable, independent variable. So instead of that, you take this scale. What is the tau is equal to omega t, right? So then what is omega? Omega taken as omega plus omega 1 form. It is a constant. The constant not function of t. It's just a constant. But constant expanded. And the solution u, it is expanded like u naught tau plus epsilon u1 tau. You take all the things into your differential equation. So in that, what happens? Highest order derivative term is there. For example, you have a differential equation. Say u double dot and plus say u equal to say function of say u comma t or u comma epsilon. You submit, for example, this type of expansions here. So then this term will get characterized as omega square. Right? Characterized omega naught square, for example, omega naught square and u double dot analyze it. That way we try to get accurate and method of this equation as usual method. It is proposed by latest method. Okay. Either you can use it, but I like this methodology with multiple steps. So this is very important to solve the hydrodynamic problems. Okay. So in which what happens? Whatever we having that independent variable, the independent variable is earlier we have given the straight particle, but here is something different. What is that here? So the take as it is taken as Tn value, Tn still Tn is equal to Tn value. It is taken as say epsilon of n and t. Okay. So for n equal to 0, we get what? What do we get? T n equal to 1, how much you get? Epsilon t. And n equal to how much you get? Epsilon t. And n equal to 3, we get epsilon t. So like that, so we keep on getting Tn value equal to epsilon n. This is the way we try to scale using this small parameters. Okay. So we have this scaling we take. Accordingly, the differential operators. Differential operators will be written in terms of chain rule, dividing. Okay. Dividing into rho by 20 naught and dx naught by dt. Okay. And this value how much? According to this is dt naught by dt. How much you get? This one. According to this here on the board. Here is so we have it very simple that dt naught by dt value is equal to 1. Here dt 1 by dt is how much? Epsilon. Okay. And here is what? So dt by dt we get as epsilon square and keep on d by dt what? D by dt you try to expand it. D by dt you can expand as say dou by dou t naught and dt naught by dt. Agree or not? Okay. And plus you take another one. Dou by dou t1 by or dt1 by dt and so on you have that. Okay. So according to this we are having this is 1 and this is what? We have epsilon and so on. It means what? Finally your d by dt value is equal to dou by dou t naught plus epsilon dou by dou t1 plus epsilon square dou by dou t2 and so on. So we get to this way. Agree? So this is the change. So we take the multiple scales. Many scales we have taken for time and accordingly. So we have this operator d by dt change in this format. So first order will be like this. How to get d square by dt square? D square by dt square means what? Whole square you take. You take second order means what? You take a square. So here is d square by dt square value will be, so you having dou by dou t naught plus epsilon dou by dou t1. Okay. So, how many scales we want accordingly, that many, so you get to the order of this. So, for example, whole square you can write directly. And then accordingly, so then your operator got changed. So, this is only one change we have. This is only one change we have. Okay. So, accordingly, so d by dt will be like this, and d square by dt square will be in this format. So, then we go to the next one is u, how to expand u. So, t got expanded, t got that is it is a function of several times like t0, t1, t2 and so on. And you see, be careful, that is this leading term started from the epsilon onwards. Okay. So, then that epsilon u1 and epsilon square u2 and like that expansion, and then accordingly you try to submit the previous this expression and then this expansion for u into your differential equation, and then we get the system of equations. So, here is what. So, then suppose if you want to stop at order of epsilon square, so then we need how many t0 t1 we need. Okay. And suppose that if you want to stop at order of epsilon cube, so then how many variables we need? t0, t1, t2. So, like that we have to calculate that how much order we want to go, accordingly we have to stop. Okay. So, this is the idea for the idea is very simple. Idea is very simple, but implementation is complicated. So, this example, if you say that this is second order equation if you take in, and then epsilon n will be written as like this 1 by n factorial f for n u naught. Actually, this is a Taylor series expansion, right? So, then we want to solve this equation, and for n equal to submit 1 here, and you get this equation. If you define in this format, n equal to, you have this type of differential equation, etc. How much time I have? We try to get it. Okay, this is sample one we have, and how to use multiple perturbation methods very effectively. Krishnendra is successful in deriving the equations and published the piece of fluids and etc. Right. Okay. So, then let us see, this method is very simple one, but able to solve great equations, right. Okay. Then now if you submit all the formalities as earlier, right. So, this is epsilon quotient equation, this is epsilon square quotient equation, epsilon cube quotient equation will be there, and this is homogeneous one, linear homogeneous, it is linear non-homogeneous, this is again linear non-homogeneous. So, whatever solution you get from here now, you submit on the right side here as earlier, and again whatever solution you get u1 and u2 from this, submit on this right side, and you get you can find out what is it. So, this is where we can proceed. Okay. So, at the leading order, so you can solve this equation leading order. So, leading order solution will be that is in the format of this we can write. Can you read or not? So, variable separable technique, if you use variable separable, here is u1 can be assumed as capital A is function of t1 comma t2, and e to power of, you can say that is m into say t0, you can assume variable separable, u1 value you can assume this. Okay. And then submit this is into your this differential equation, and then you can receive this is solution which is in this form. Okay, it is in this form. So, we do not have initial condition, I told you already, that is instead of initial conditions, these solutions can include the parameter epsilon. Okay, that includes the parameter epsilon here, t1 t2 has the parameter epsilon. Okay. So, u1 we get in this format, and then what is A here? A is amplitude, we can call it amplitude we have, and function of t1 t2, it is constant we can say, and what is t0 here? T0 is the variable we having which is equal to t. T0 is what? Here is, here you can say T0 is fast variable and T1, T2 are the slow variables because epsilon is connected. Okay. So, we have this is the solution. What is A bar here? A is, we say that it is a complex function, A bar is a complex conjugate amplitude. So, therefore, totally we have u1 value will be expressed as this. Can you say it is real or complex u1? If you have z is a complex variable plus z bar you have complex conjugate, what do you get? Z is complex number, z bar is complex conjugate. Z plus z bar how much? What is real or complex? Real. So, here the same thing, this is the complex function, complex solution plus its conjugate. So, finally, u1 is what? Real. real. So what are A here? A is amplitude, which is depends on T1, T2. Now what we have to find out? What we have to find here? We have to find what are the A, capital A. Okay, so then for this is let us see this, take the second equation. Take the second equation, and you know that what is the value u1, you know that, submit here, and then you have that is e to power phi t naught I omega naught t naught, and this is the first harmonic, these are the second harmonic. E to power phi omega naught is first harmonic, sin omega naught t plus I, cos omega naught t plus I sin omega naught t. So first harmonics we have both, and here is what, e to power 2I omega naught t, second harmonic. Okay, so then what happens, now we want to solve this, but due to this operator, I told you na, this is you have to take to the denominator. Okay, so if you take this is to the denominator, so this term, first term is going to give the secular term. First term gives the secular term. Okay, so then what happens, we have, so for such it is giving secular term, so we have to remove this secular term from here. Okay, so for that, what d1a must be equal to 0, right? So if you make it, so then d1a must be 0. So what is d1a? dA by dt1, a is a function of t1, t2. A is a function of t1, t2. But here it is showing that with respect to t1 it is 0. It means what? It is a function of only t2, not t1. So therefore we have only t2, and then accordingly we having, now this is only term is left. Now this is only one term is left. This is we have made 0. Then how to get u2 here? How to get u2? U2 how to get? According to this is u2 something did by your operator. So it means what, u2 is equal to this everything did by the operator d naught square by omega naught square. So that is gives you u2. Understood? That is gives you u2. So this is where you try to get this u2 value. Okay, and go to the next one thing is that whatever you having the other cases given here, then you go to next order. Okay, this is very important information, that is why the initial condition ignored here. You can see that n greater than 2, so we obtain or choose a that is constants un from the conditions. We can choose that from the condition, we can choose it. And next thing is what here is we can ignore the whatever we have in the initial conditions. That is how your amplitude is including the epsilon. A is function of t1, t2. Okay, that is epsilon will come there. So this is one thing. Next level is what? u1 we know, u2 we know, and d1 is 0. So using this third equation as earlier, then what happens? This first term is what? It is again you have d square, d naught square, and omega naught square we having as like this, and right side is what? First harmonic. That this will give the secular term. It gives infinity. Okay, but remaining third harmonic we having, so that will not give. So hence what happens? This is bracket value must be 0, so that is 0 here. And now you have to solve this equation. This is ninth equation, but here solving is not easy. Then take the your complex format. Okay, complex format. What is complex number? Z is equal to r e to the power phi theta. Right? Use that approach and then submit it to the equation and separate real part and imaginary part. And from here you get dA by dt2 is 0. Because omega not equal to 0, so this contribution will be 0 means what? A is a constant here. Okay, but this another equation is in terms of beta we have. So here what A is what? A is function of t2, beta is function of t2. We got A value is a constant, but beta you can find. So if you solve this is, then you get beta value in this format. It still has a constant. Okay, and that's how we know the A value, we know beta value, submit, and t2 we know that, submit into capital A. What is capital A? Capital A, capital A is what? Capital A is equal to A by 2 e to the power phi beta. We know what is A value, what is beta value from this. And then if you submit here, A value we have this. Okay. And capital T what? T2 is replaced by epsilon square T, it is the original scaling. And like this we have an amplitude here. So we know A value finally. A value, where did we get? Where did we get A value now? At the order of epsilon square we got A value, which is independent of T1 we got A. We don't have clear picture, but here we got completely what is A. It is function of just a T2. Okay, and then what happens when we know that, submit into your solution. What is solution? Yeah. So into this is into this. Uh, yes. Yeah. Into this where we have written solution, not written. Okay. If you not written, okay. So then okay. We try to submit these values here, and then we get the result solutions like u value is equal to that is epsilon u naught and something like this. You submit all the values. This is u1, this is u2, okay, epsilon cube. Okay, so the solution is ready. You can compare with the, these are the arbitrary constants we having a and beta naught that can be removed if you know that the exact condition. So like that we have, oh, when it is. So this idea is, this is only the idea to how to implement the multiple scale analysis. Christian is successful in publishing the paper using this method only, phase of read. Okay, so this is only the idea, but the things are different. Okay, so like this, what happens? We can apply to the some real world problems like your Lebanon problem, and find out this Landau-Ginzburg equation as shown. You know, same whatever you have now. So this is the if you go to this, yeah. Yes. Hmm. Yes. So this is the equation you have now. Oh, it is not coming. I'm sorry. What to do? Okay. Okay. Now it is okay. Right. Now you can see that this is multiple scale analysis. Right. So taken x values epsilon x and y value epsilon y and t is equal to epsilon square t, for example, and then you can have this expansion peacefully like epsilon f naught and so on, and finally you can receive in this format. This is the equation, and one can solve it. Okay, it is according to multiple scale analysis. Right. So this type of solutions you can catch for the Landau-Ginzburg equation if you solve it. Okay. I hope you understood, all of you. Huh? Yeah, of course. I was kept inside of some of the variable, right? I don't like scaling. I scaled it and maybe, right? Okay. So this is the way one can solve this one. I hope. Yeah. Okay. Any notes, please? I hope that I finished in time. Right. This is madam has done for the rotating case, rotating geometry using liquid gallium and etc. Right. Okay. Any notes, please? This is about the perturbation methods of regular perturbation methods, and if you are interested, you can study the singular perturbation methods, and that is valid only in the boundary layer region. Do you know boundary layers? Boundary layers, the layers which are very connected to the your boundary of the region. Okay, maybe solid boundary, free boundary. So that region you can call as a boundary layer, where the variations of viscosity will be say 90%, for example, but 10% will be lower in the rest of the region. So that region we call as a boundary layer. That much thickness we can go up to this much. It is may not be defined as this much thickness we don't know, but variation should be. Viscosity variation should be 90% and 10% in the rest of the region. So how much width of that layer is there, that we call as the boundary layer with 90% changes in the properties. Okay, it is called a boundary layer. So there one can use the single perturbation method and look at that. So this classes does not include the single perturbation. So I hope that you might have small information I able to inject you about perturbation method and its importance. Right? Okay. Any doubts, please? Examination will be connected on this schedule.